Hi everyone, in this video we are going to be learning about chords, tangents, and secants, and finding missing segment lengths within circles. So there are several different ways to find missing segment lengths in circles, and it depends what type of line segments that you have. So if you look at our chart here, we have four options. We could have two intersecting chords, we could have two tangents, two secants, or one tangent and one secant. These are going to be the common scenarios that we see and the ones we'll be working through in this video today. So for intersecting chords, the rule is that you are going to multiply the two pieces of one chord, and that's going to equal the product of the two pieces of the other chord. So in order to kind of write that in our picture, I'm going to label one chord, the two parts, as A and B, and the other as C and D. So the rule would be multiply the two parts of one chord, multiply the two parts of the other chord, and those will be equal to each other, those two products. Okay, so again, the important rule is that the first two things you multiply should be from the first chord, the same chord, and the other two pieces you multiply should be from the second chord. If we have two tangents, this one is quite simple, that two tangents that meet at the same external point are just equal to each other. Okay, there's nothing more to do there. Okay, so if I labeled one as A and one as B, we would just say, okay, A is equal to B. All right, if we have two secants, here's what we're going to take important note of. That if I zoom in on this picture and I look at one of the secants, there's always going to be a piece that's outside the circle, and there's going to be a piece of the other secant that's outside the circle. Then we have the whole entire secant, and we have the whole entire secant. Okay. So when we look at this, we're going to pay attention to the outer parts, the outsides, and the whole thing. We are not going to use the piece that's inside the circle as part of our formula rule here. So the rule is going to be that you're going to multiply the outer part of one secant times its whole thing, and the outer part of one secant times the whole thing. And just like the chord one we saw before, we want to pay attention and realize that these should be from the same segment. So outer times whole, that's going to be from that first secant, and the outer times the whole over here is going to be from the other secant. All right, our last scenario is if we have one tangent and one secant. So this is our tangent here. Remember, the tangent just touches the outside of the circle. It doesn't cut through it. And for the secant, I'm going to put the same labels. So I'm going to have the outer piece and then the whole entire thing. So the rule for one tangent, one secant, for the secant, we're going to do the same rule from before, outer times whole. But the tangent, the outer and the whole are the same thing. So the way we write this is saying outer times whole is equal to the tangent squared. And these are basically our four formulas that we're going to be using throughout this lesson today to find missing segment lengths within circles. All right, so let's take a look at some examples. You might want to have your calculator handy. All right, number one. If AE is 6, I'm going to label as I read, CE is 4, and DE is 3. Find the length of BE. Since I'm looking for BE, I'm just going to put an X there. All right, so we definitely have this scenario here that it's two intersecting chords. So remember our formula, multiply the two parts of one chord, multiply the two parts of the other chord. So 4 and 6 multiplied is going to be equal to 3 times X. And then you have a very quick algebraic equation to solve here, and we get that X, or BE, is equal to 8. Number 2, if AB is equal to X plus 5, every time I read a question, I'm going to label as I talk here, and BC is 3X minus 2, solve for X. Well, this is the scenario where you have two tangents that meet at the same external point, and that means they're equal to each other. So X plus 5 is equal to 3X minus 2. And I'm going to get my variables on the same side and my numbers on the same side. So I have 7 is equal to 2x when I divide by 2. I'm going to get that x is equal to 3.5 in this case. So again, if you have two tangents that meet at the same external point, we are just going to set them equal to each other. Number 3, BC is 5, AC is 12. When you're labeling that whole thing, put a nice big bracket there so it doesn't get confusing. CD is 4, and we're looking for the length of CE. So I'm going to put X there. This is definitely the 2 secant option. Notice both line segments cut through the circle. And that rule is the outer times the whole equals the outer times the whole. So look at the top secant AC. The outer piece is 5. The whole thing is 12. With the bottom secant, the outer piece is 4. The whole thing is X. So this is going to be 60 is equal to 4x when I simplify that. And if I divide by 4, I get that x is equal to 15. For number 4, when I look at this picture, I see that this is the tangent secant option. So BC is 4, CD is 5, BA we're looking for, so I'm going to call that x. All right, so this question brings a point to our attention that we have to just pay attention to when we are looking at secants. So the rule is outer times whole. So the outer is 4, but the whole thing is not 5. The whole thing wasn't given to us, but we can quickly find it by just adding those pieces together. Then that's equal to tangent squared. So 36 equals x squared, and we get that x, or BA, is equal to 6. So again, just pay attention to the fact that this question didn't give us the whole secant, but we can quickly find it just by adding the 2 components. All right, we're going to continue to look at some more problems utilizing the segment rules. CE is, in number 5, CE is 5, AE is 12, BE is 10, and we're looking for DE. So we're going to multiply the 2 parts of one secant, multiply the 2 parts of the other. I get 60 is equal to 10x, and x is equal to 6. Number 6 looks a little different. So we know AB is 4, BC is 5, DE is 6. And we're going to find the perimeter of triangle ACE. To do this question, I'm going to just add a little highlighting in here, and I want you to notice that FA and BA are 2 tangents that meet at the same external point. BC and DC are also 2 tangents that meet at the same external point. And FE and DE, 2 tangents that meet at the same external point. So remember, if you have that scenario, those 2 tangents are equal to each other. So the 2 tangents that I highlighted in blue are going to be equal, and they're both 4. The 2 that I highlighted in green, both equal at 5. And the 2 I highlighted in pink, both equal at 6. So if I'm going to find the perimeter of triangle ACE, I'm going to be adding up all these pieces. So 4 plus 4, my 2 blue pieces, 5 plus 5, 2 green, and 6 plus 6, the 2 pink ones, and I get that my perimeter is 30 units. Number 7, we know CD is a tangent, CB is 4, BA is 6, and we're going to find the length of CD in simplest radical form. Notice again, like the question before, we weren't given this whole secant, but we can find it really quickly by just adding 4 and 6 together. So the rule for one tangent, one secant, is outer times whole, so 4 times 10 equals tangent squared. Okay, so that's going to give me 40 equals x squared, and when I take the square root, I'm going to get that x is radical 40. But this question asks us to put this in simplest radical form. That means we are going to have to break down this radical and think about a perfect square that goes into 40. The perfect square that goes into it is 4, making the missing factor 10. So in simplest radical form, I get 2 radical 10 as the value of x, or as CD. Again, when you're putting something in simplest radical form, you're going to look for 2 factors of that value, and one of them must be a perfect square. Okay, number 8. I look at the picture and I see that I have two secants here. Notice LN is going through the circle, not just touching the edge. So at first glance, it might look like a tangent, but it is a secant as well. All right, LK is 3, KJ 5, LM is 4, and we're going to look for the length of LN. So I will put X there with my bracket. I'm going to quickly add in that the whole segment up here is 8. And now let's use our rule for two secants. Outer times the whole, 3 times 8. Outer times the whole, 4 times X. And I can quickly solve this, and I get that X is equal to 6. Number 9, I have 2 intersecting chords. Okay, so anytime you're looking at a new question, take note as to what situation you have in terms of what type of segments. All right, AE is 4. Notice this next piece, AC is 14. So you can do this if you want, make a big bracket. I'll show you the other option in a second. DE is 8, and this is going to be X over here. All right, so if that option doesn't work for you and that looks a little confusing with that big bracket, what you could also do is just subtract 14 and 4, and we would get 10, and just fill the 10 in here for the length of EC. So if AC is 14, I can infer then that EC is 10. The reason that we can do this here and subtract is because the rule is we're going to multiply the 2 parts of one chord, and those 2 parts are 4 and 10, not 4 and 14. Then I'm going to multiply 8 and X, so I have 40 equals 8X, and X is equal to 5. Number 10. This looks a little different. It says AC and DB are perpendicular. AC is 8. And OE is 3, and find the length of OB. Okay, so if I'm looking at this here, I noticed that it gave me that AC is 8. I don't want to do that big bracket, just like I showed you in the previous problem. What I want to do instead is split it. So I'm going to put 4 here and 4 here. So the reason I can do this is because segment DB is definitely a diameter here, and that means that it's splitting the circle in half. Basically, it becomes the perpendicular bisector of AC. So I know that that can be split 4 and 4. When I look to find the length of OB, it might not be obvious as to what to do on this question. So when I'm looking at this, what I'm going to do, I'm going to add in a different color, is I'm going to find the length of OA. Okay, and I understand that's not what the question's asking for, but I'm going to find that first, and I'll show you how it relates. The reason I want to do that is because, going back here with my highlighter, I'm basically creating a right triangle here. And I'm looking at a right triangle that has legs of 3 and 4, and you might know that as a Pythagorean triple, that means the hypotenuse is going to be 5. If you don't know that, you can always do Pythagorean theorem and do 3 squared plus 4 squared equals c squared, and you'll get 25 equals c squared, or 5 is c. Here's why that this is helpful to me. OA, if we look at it, is a radius. Okay, a radius goes from the center of a circle to the end of a circle, to some point on the edge of the circle. Every radius in a circle is the same length. So if I drew OC, for instance, it would also be 5. So if I'm finding the length of OB, right, and I'm looking at this over here, I know that that's a radius, and so OB has to be 5 as well. And I actually didn't end up using any of my circle rules from before, but I just used Pythagorean theorem and knowing that the radii are always going to be congruent. All right, let's say that I wanted to use one of my circle rules from before. I'll show you how you could do that. Let me just draw this out here. If I have a circle and I drew this in here, and I'm going to draw my diameter in. Okay. I actually know that OD is 5, right? Because again, the radii are all congruent. OD is a radius. So if you look from D to where the chords meet, that's really 8. It's 5 and 3. This over here is X, and these were 4 and 4. So if I solve that, 8x equals 4 times 4, I get 8x is 16 and x is 2. Okay, here's how that relates. If I go back to my picture and I fill in that EB is 2, now you can see that OB is 5 because it's 3 plus 2. Okay, so you could use one of those circle rules if you wanted to as well. All right, couple more here. Number 11, CB is 8, CA, whole thing, 20. CE, the whole thing is 16, and we're looking for the other outer piece, CD. All right, 2 secants, so my rule is 8 outer times whole, so 8 times 20, outer times whole, x times 16. So over here, I'm going to get 160 equals 16x. Divide both sides by 16, and I get x, the length of CD, is going to be 10. Okay, for our last question, 12, we are going to have to draw the picture ourselves. So secants PQR and PST are drawn to circle O from external point P. All right, so let's start by drawing a circle. We know that the center is O, and we know that the external point is P. We know that from P, there are 2 secants, and we know their names are PQR and PST. So I'm just going to make the top one PQR. So PQR and PST. Okay, so just make sure the letters go in order. So Q shouldn't be between P and R, for instance. All right, now let's label. PQ is 8. RQ is 4. This doesn't look drawn to scale, but that's okay when we're making our own pictures. PS is 6, and we're looking for the length of PT, so I'm going to put a big bracket there with an X. Now for the length of RP, I'm going to put a big bracket in here as well, add the 2 pieces and get 12. So for 2 secants, our rule is outside times the whole thing equals outside times the whole thing. All right, so 8 times 12 is going to give us 96, 6x over on the right, divide by 6, and we're going to get that x is equal to 16. Okay, hopefully in this video you understand a little bit more about the different segment rules that go along with circles. If you're looking for the different arc and angle rules that go along with circles, that's the previous video in this playlist. And thanks for watching, everybody.